evening, everyone. Welcome to the fourth lecture of our study seminar series. May we now invite our Dean of College of Business, Professor Human-Induced, to deliver an opening speech for us. Professor Yan, please.
I guess today it's a change, and we changed the channel. In a way, today the seminar is going to be conducted in English. We were having a 3 Chinese lecture, but today we are going to conduct it in English. And let me, sort of give a little bit of introduction about this seminar series. And this is organized by College of Business, and we are all, College of Business. All our education are to some extent related to the business. However, there's a considerable call for social responsibility, sustainability, and many other things. And we want to us putting those things into a business education. So therefore, we thought about it, and let us also do something about it. So this is a seminar series. The intention is to talk about the science engineering, talk about the technology, talk about the literature, talk about history, anything but business. So today, we have a talk on this global warming matter, and this is very much, the sustainability, domain of sustainability. So we come up with this, if you look at the names of our series, series, we call this 席明纳. That is the early translation of the seminar. So I guess this is what exactly we are doing. And we sit together and we try to understand some matters and to the end. And we hope everyone takes something back, to learn something from this. Okay? So today we are excited, and we have Professor Johnny Chen, 陈仲良教授来给我们讲讲这个 global warming 的事情。尽管这个是用英文讲的，大家如果愿意用中文提问、广东话，陈教授都没问题的。陈教授是客气，他其实是可以是用 absolutely I know you can talk about this thing in Chinese。所以这个我这个就让这个康妮来，是吧？康妮你来介绍陈教授是吧 ？OK， 所以我们每个人都分担一点工作。Thank you for coming.
Thank you, everyone, and thank you, Professor Johnny Chen. To kick off today's seminar, may I take a minute to introduce our honorable guest speaker to you. Professor Chen is currently the Dean of the School of Energy and Environment. He is also the Chair Professor of Atmospheric Science. He is also the Director of Guy Carpenter Asia Pacific Climate Impact Center of our CityU. Professor Chen is internationally renowned in the research areas of typhoons and monsoons and has published over 160 SCI journal articles. Recently, he has been working on the problem of global warming and typhoon activity relationships, as well as on tropical cyclone and monsoon climate. He is currently chair of the Tropical Cyclone Panel of the Tropical Meteorology Organization Tropical Research Working Group. He is an honorary fellow of the UK Energy Institute, a fellow of the American Meteorological Society, and a recipient of the International Journal of Climatology Award of the Royal Meteorological Society. May we now invite Professor Chen to sign on our pop-up wall and start today's sharing section.
Okay, thank you very much for coming in the evening. I hope you had something to eat outside. and it's not too cold tonight. All right, so Professor Yan asked me to give a talk, and this talk I actually gave last year as the CTU presidential lecture, and I guess Professor Yan probably fell asleep that time, so he wanted me to give it again. So I hope he won't fall asleep this time. Anyway, so the idea of this talk is to ask about this question, global warming. So everybody knows about global warming. But the question is whether it is natural or human-induced. So this is the question we want to address. I hope I'm going to go back and forth in terms of the pointer, and so people sitting on that side will not have to have the neck on one side all the time, okay? So the outline of the talk is that I will start out with the science of global warming. I know many of you may not be scientists, so I will be very simple in terms of science. And then I want to talk a little bit about global warming from a historical perspective. Many times we look at from a very short period, and then we want to see, okay, if we go for a long period of time, what happened? What actually had happened? And then I'll talk about natural versus human-induced, and tell you something about the effects and projection of the future effects. Okay, so we'll start with this cartoon here. I like this cartoon very much. Is that it says, the kid asked the professor, is global warming natural or human-induced? And so the professor said, well, I'm not sure. So let's ask the global warming theory. So what did the global warming theory say? So this is an inconvenient truth that some people would say that, look, it's all these climate scientists who come out with this idea that the globe is warming. It's not. It's just they're just making it up. Now, if you live in a cold country, in either like right now in the U.S., it's snowing very heavily, and so you've asked the people in the U.S., is it global warming? They say, what are you talking about? You must be kidding. Well, I have to shovel my snow off my car every day. So it's not global warming. So if you are living in the U.S. today, you would say that this is why I do not believe in global warming. What are you talking about? Right? And then the other thing is 2 years ago, there's in Iceland, there is this volcano explosion. And so they said, well, if you say man is causing global warming, then what are you talking about? This is all this explosion going on. That's natural. That's nothing to do with human activities. And so, of course, there's also these people who said that it doesn't, there's no such thing as human-induced global warming. It's all natural. So rising sea level cannot be considered as a result until water reaches the ceiling, or something like this. So this is some kind of a joke, or actually many people would say that this is natural and not human-induced. And in fact, just about 40 years ago, this is actually a report in Time magazine, and it says whether there is another ice age going on. So it says that during 1972, record rains in parts of the U.S. have caused some of the worst flooding, and a series of unusually cold winters has gripped the American far west. So at that time, Time magazine puts out this as their front cover. So it's the big freeze. So this is the Time magazine cover in December 1973. So at that time, people were talking about how do we warm the earth so that we will not be going into an ice age. Okay? But then a few years later, in 1977, then they came up with another one that says the Global Warming Survival Guide. So people have very short memories, and they're looking at very short time scales as to what's going on. All right? So what actually is going on is that what you see in here is the temperature, the average global temperature between 1850 to 2014. So this is the latest, all the way up to October of 2014. Okay? Now, what we're plotting here is this. The zero line means the average temperature of 1961 to 1990. So in other words, if you stay on this line, you will be at a temperature that's the average between 1961 and 1990. Anything below this line means that it is cooler, and anything above this line is warmer. Now, there are three different lines in here. So there's the Meteorological Office, which is the UK Meteorological Office, and NOAA is the US, and then NASA is also the US. And so they're taking data from different places, and so therefore there is some difference. Nevertheless, you can see in here that they all agree with one another, and so you see that in the late 19th century, it is below normal, below this line here, and then it starts to rise in about 1900. Now, and interestingly, there is this drop. In fact, this is the time when people were talking about the next ice age, because you see that the temperature were dropping. So you see that, so people were saying, look, it must be another ice age coming. But then it went back up again, and now in the last 10 years actually have been the warmest for a long time, and I'll show that to you later. Okay. So when you start looking at these short time variations, then you would have a different perspective. Now, so what is causing this? And to understand this, let's do a little bit of science in here, because very, very basic science. In the maybe you have learned this in your high school physics sometime, is that every object will emit some kind of energy. Okay, and the amount of energy depends on the temperature of the object. So, for example, here this is the amount of energy parallel to and the x-axis is the wavelength. So for the sun, because the temperature is very high, the energy distribution is like this. However, for the Earth, because Earth is a lot cooler, so therefore the energy distribution is like this. Now, for us, for our eyes, we can see this part. This is called the visible part of the spectrum. So that and because the sun has this in the peak, so therefore we can see during the day when there is sun. So that's why you have this one here. Now, what's important is this, that if you look at the energy that's being absorbed by different gases in the atmosphere, so what we are plotting here is that it's called the atmospheric absorption spectrum. So if it's 100%, that means it's total absorption. Nothing comes through to the atmosphere. At 0% means total transparency. So we have plotted, this is the black one is total, and then you have the red one is oxygen plus ozone. The green one is CO2, and then H2O at the bottom here. Now, what's interesting is let's put the visible spectrum back in here. So what you see in here is that in this part of the spectrum, there is almost zero absorption, right? There's no absorption here, no absorption here. Beyond this one here, this is the ultraviolet, and there is almost complete absorption by oxygen and ozone. And you need to think the presence of ozone in here, because otherwise every one of us will get skin cancer, because ozone absorbs the ultraviolet radiation so that we don't get skin cancer. And that's why you might have heard about the ozone hole because of that. Now, but then what's interesting is that after this one here, then you start having this absorption, right? You have these peaks in here. And this is the peak. Most of this absorption is what we call in the infrared spectrum, the infrared part of the spectrum. And so the absorption then is, most of the absorption of the energy here is in the infrared part of the spectrum, right? And infrared part of the spectrum is where the energy coming from the Earth is coming out. Okay, so this is the peak in here. So we have quite a bit of absorption in here. Now, if you expand this to other gases, it will be the same thing. So in addition to CO2, you will also have the top part here is methane, nitrous oxide, and they all have absorption in this part of the spectrum where the energy from the Earth is coming out. Okay? So that means if you have the energy from the Earth coming out, but in the atmosphere, all these gases are sitting there, and so then they absorb the energy. They don't let the energy to go back out to space. Right? So this is what is known as the greenhouse effect. So the greenhouse effect basically says that, okay, you have the sunlight coming in through the atmosphere, warms up the Earth's surface, then the energy is then given out back by the Earth, but then this is the, some of the infrared is trapped by the gases in the atmosphere, reducing the cooling, and most of it goes back into the atmosphere. And so, but if you have a lot of these gases in the atmosphere, then it traps more heat, and so it's called the greenhouse effect in the atmosphere. So why do we call this a greenhouse effect? Because a greenhouse is something like this. For those who have not seen a greenhouse, it's for growing plants and vegetables or whatever in the winter time, right? So what happens is that in the greenhouse effect is that basically that you allow visible energy from the sun to pass through the glass roof here, or glass walls, but then the glass prevents the heat that's generated in here from going back out, or partly reflected by the glass, so therefore it is trapped inside the greenhouse, and so as a result you will have the heat being trapped in that. So that's why the gases in the atmosphere are called the greenhouse gases, because they have the same effect as an actual greenhouse. So they trap, these gases will therefore trap the heat that's being emitted by the atmosphere, and as it traps it, so therefore the Earth temperature increases. Okay? So that's why it's called a greenhouse. And the three main culprits of greenhouse gases would be CO2, carbon dioxide, methane, and nitrous oxide. And this is the amount of CO2, methane, and nitrous oxide from the 1700s all the way to today. So you can see that there is a steady rise, but the most significant rise is in the last 50 years or so. In fact, if you blow this up, you will see that even in the last 10,000 years, the CO2 or methane or N2O really hadn't changed very much except this last part here. Okay? So what you saw just now is, you can expand this and to see it in here. That in the last 10,000 years, the rise has been the most significant in the last 50 years. And this is sometimes called the hockey stick, because it looks like a hockey stick. So it's shot up very significantly. So this is you can see that the amount of CO2 has, the amount of these three types of gases have increased tremendously, and as a result, you have much more energy being trapped in the atmosphere, and therefore you have the warming. And this is the latest report from the IPCC, which is the Intergovernmental Panel on Climate Change, from the United Nations. And what is plotted here is it's a very complicated plot. But what I want to show you is what is plotted here is anything on the right-hand side of this line, zero line here, means that it is warming the Earth. Okay? And anything that's to the left of the zero line means that it is cooling the Earth. Okay? Now, so what you see here is that this first few rows here is the different types of gases, CO2, methane, and nitrous oxide, and so on. And they all contribute to a warming of the atmosphere. And notice on the rightmost column, it says level of confidence, right? The level of confidence here. VH means very high confidence. H means high. So what you see here is that in this first column, they're all very high. That means we have very high confidence. That means it's over 95% certain that these gases will contribute to, or has contributed towards an increase in the temperature. And how much has it contributed is in the length of the bar. Now, every part here, there is this error bar here, and you probably have noticed that in all the data studies that must be an error, uncertainty here. So this is the uncertainty here. Nevertheless, you can see that they are all positive, and if you sum all these up, you will see that at the bottom, the red bars here, that in 2011, compared with 1750, there is an increase of about 2 units. All right, so 2 units, watts per meter square, it's the unit that we use. And what does that mean? What does 2 mean? Okay, you think about this every day. Actually, the Earth emits back into the atmosphere about 300 watts per square meter, 300 units. So then you say, so what's 2 units? It's only 1% or less than 1% of what's the energy that's going back in there. But the thing is, it's 2 units every day. So it's not just 2 units, but 2 units every day sitting here. Right? So for 1 year, it will be 600 units sitting in here, in the Earth. Right? So it's contributing to that. So it's not just the 2 units that's important, but it's the cumulative effect every day that happens. And so what you see in here is that you will have this amount of warming contributed by these. Now later on we'll come back and talk about these negative bars in here, which is some of the cooling effects that we will talk about a little bit later. Okay, so remember that we have this contribution. All right, now let's go back to this graph here. What I want to do now is just to lead you back into history. Let's go back to history. I don't know if your seminar had talked about, I guess Zheng Pei Kai probably talked about history or something. So we'll go to history, okay? So how do we go to history? Now, you see that this is from 1850 to today. So now let's try to shrink this. And then put it into perspective for the last 2,000 years. So instead of the last 150 years, we have the last 2,000 years. Okay, so in the last 2,000 years, this is the temperature record. All right, again, 0 is about the average. So what you see in this, what I show you in the last 150 years is in this gray box that I just showed you before. So this part here. Okay. Now, if you go back to the last 2,000 years, what you see here is that there actually have been times when it is just as warm as today, right? So this is actually known as the medieval warm period. And in fact, that's the period when the Vikings actually went to Greenland. So if you learn about history, that you see this. And then when it becomes too cold, then this is the end of the Viking colonization of Greenland. And actually there was this period here in the 1400s to the 1700s, that's actually known as the Little Ice Age. Okay? So there have been these changes. Now, just to, maybe some of you are good in Chinese history, so I'll put up the different dynasties in China, for China. And you can see this, that in different periods, for example, the Tang Dynasty is this period here. The Tang Dynasty is this period. And we knew that the Tang Dynasty is probably one of the most prosperous dynasties in China. And it might have something to do with the temperature being warmer. And the Ming Dynasty was one of the worst dynasties. And it may be because it's very cold most of the time. So, cold means that you have lots of drought, lots of famines, and so on. So people were not happy, and so therefore there's constant unrest in the Ming Dynasty. So this is something that's interesting for the historians if you want to look at the temperatures. All right, so enough of history, Chinese history. All right, so let's go on. So this is the last 2,000 years. So let's shrink it a little bit more. Let's go to the last 10,000 years. All right, so again, this is the last 2,000 years. Now, and the temperature is it also fluctuates, right? So it fluctuates up and down like this. And until about 10,000 years ago, this is what we call the last glacial period. So that's the end of the last glacial period, and starts to warm up, and then come cool again, and so on. So if you look at this, that means throughout history, temperatures have been oscillating up and down. It's never going straight up or never going straight down, right? And by the way, so this is called the Roman climate optimal. And you remember the Romans at that time, if you looked at all the drawings or movies, the Romans never had to wear very thick clothes, right? So it's really warm at that time, most of the time. Now, let's go one step more. And let's go to the last 400,000 years. Okay? Now, this is what happened in the temperature in the last 4,000 years. And this little part, again, is the last 10,000. So you see that every time, every so often, you will have these oscillations. Right? And the period is roughly about 100,000 years, like this. Now, so at that time, of course, there was no human civilization. So there was no such thing as industrial revolution. No such thing as the generation of greenhouse gases by humans. So what is the CO2 concentration like in those times? So if you look at the CO2 concentration, it's like this. All right? Now, and today, of course, it's going to close to 400 now. So if you put these two together, you find that they match very well. That means it is true that throughout history, that if you have a CO2 increase, then the temperature of the Earth gets warmer. If you have a CO2 decrease, the temperature gets cooler. Now, but interestingly, you look at this graph here. Now, I moved the two graphs so that they match quite well, right? But what about this one here that we have today? How come the temperature is not increasing just like previously? So in fact, even if with so much more CO2 in the atmosphere, the temperature has only increased to like the previous peaks, right? And this is one of the reasons why the climate skeptics say, look, this has happened before, so what? So CO2 has increased so much, but the temperature hasn't increased, right? So why bother? Right? So you can think about whether you now become a climate denier or climate skeptic now, after I've talked about this. All right, so before I explain this one here, let me try to explain a little bit of what is causing these oscillations. Okay? What is causing all these oscillations here? Now, there is something called the Milankovitch cycles, and this is a East European scientist who discovered that the Earth, when it rotates around the sun, the way that it rotates has different features during different periods of the Earth and the sun. So the first one is what we call a precession of the equinox. Now, you know the equinox means that it's the time when the sun is supposed to be shining right on the equator. Okay? So sometimes what happens is that and because the reason why you have this precession of equinox is because the axis of the Earth relative to the plane of the ecliptic, which is the plane of rotation, can flip. So sometimes it flips this way, sometimes it flips this way. So that means the amount of energy that's received by the Earth from the sun will change. And this flip has an oscillation period of about 19,000. K means 1,000, so it's 19,000 to 23,000 years. So every so often it has this flip. The second effect is what we call the obliquity, which is how much tilt the axis of rotation of the Earth. relative to the vertical. This vertical actually means the normal to this plane of rotation. So sometimes it tilts more, sometimes it tilts less. So if it tilts more, the difference between the summer and the winter is more. If it tilts less, then there's less difference. And there is a cycle of about 41,000 years. Now the last one is that the orbit of the Earth around the Sun sometimes is more elliptical, sometimes it's more circular. So if it's more elliptical, then between the winter and the summer, there's a much larger difference. If it's completely circular, there's no, every season is exactly the same. They receive the same amount of energy. So if you plot these variations against the stages of this glaciation for the last 1 million years, then if you add these three together, they basically match the stages of glaciation. So in other words, these three oscillations basically explains why we have these oscillations in terms of the temperature. So now you ask the question is, how do you get these measurements? There was no human being at the time. Obviously no thermometers. So how do we get these measurements? And this is something that's very interesting. It's something called what we call a paleoclimatological techniques. Paleo means for a long time. So how do we do this? A very popular way of doing this is to drill a core into the ice. So this is a lot of people. This is done in Greenland and many other cold places. So they drill a hole and get a cylinder of ice. So you got an ice core, taking it out. So what does it tell you? Because every time you have the winter, so you have ice or snow deposited. So if you have lots of pollens, if you have very strong winds, or if you have different changes in terms of the amount of rain, amount of snow, then by looking at the how much the amount of different chemicals in there, you will be able to estimate the temperature. So this is an example of this. So for example, this is a depth of 53 to 54 meters. You have these layers here, but not very clear, right? If you go deeper to about 1800 meters, then you see these layers here. And then by doing chemical analysis, then you will be able to know whether this period is cooler or warmer, depending on how much snow that's being deposited in that column. And then you can go even further. So you dig deeper, that means it's earlier. Okay? So that's one way to do this. Many people are doing this in that community. Of course, you can do the same thing in the ocean, not just in overland. You can do this in the ocean. You drill a hole through the core, and then you can still get very similar things. Or you can do it in a lake. The lake sediments, if you have, especially near the ocean, if you have many typhoons, then you will sweep a lot of dead fish and dead shrimp and whatever onto the shore, and then they get deposited into a lake. And then the next year you have another one, so you have different layers, and so you get a core, and then you get very similar results, and then you can estimate the number of typhoons, or whether you have very strong rain and so on. So this is one example of this core. Then you can see that there are also different layers, and then you can do some chemical analysis to get that. Another very popular way is to look at tree rings. Now trees grow every year it will grow, and then if there is a lot of rain, then there's a lot of support or lots of rain and sunshine, then you will get more growth. The tree will get more growth, and so therefore the distance between one ring and the next becomes wider. And but if it's very dry, the tree will not grow very much. So the distance between the two rings will be very small. So by looking at that, you'll be able to estimate whether there is how much rain there is in that part. Or you can go to a cave. If you go to a cave, these are the stalactites and stalagmites. So the drip from the top and the build-up of this stalagmites in the bottom will be able to tell you how much rain there is. And in fact, people have looked at this, that different types of rain can give different types of chemicals in that. So you can also do that. Or you can look at coral growth. If you're going to look at coral growth, you can still see that. Okay, so this is some of the methods in which you can estimate the temperature many thousands and millions of years ago. Okay, but of course, as you go further back in time, the less accurate you will be. There will be more uncertainty. All right, so this is how you get this. So I come back to this graph and ask you, why do we have this one here? That even though the CO2 concentration has gone up so much, the warming really hasn't happened like previously. And then to do this, we come back to this chart that I showed you earlier. Remember I said you have this negative things here, right? So what are these negative? This is aerosols. So mineral dust and other aerosols. Aerosols means particles in the atmosphere. Okay, so these are particles in the atmosphere. Now, there are two types of particles in the atmosphere. One is those that are from nature, like volcano eruption. And there is also a second type of aerosols, which are what you see outside, pollution in Hong Kong or in many places in the world. So they would all then contribute towards the cooling of the Earth. Okay, if there were no such particles in the atmosphere, then it will actually be warmer. All right, so to show you this, so for example, this is just the expanded version of this, and you see this. So volcanic eruption spews out a lot of particles into the atmosphere, and these particles are way up in the atmosphere, and so when the sun comes down, these particles will then scatter the solar energy back into the outer space. It will not come to Earth, so therefore it would cool. And so this is what, as cartoon showing that you have eruption, so you have a lot of these particles, and so although it will still trap some of the infrared radiation, but it will lead also to a lot of cooling. Now, to demonstrate two recent examples, there were two big volcano eruptions in the last century, or a few of these. So this is the Argon volcano, El Chichon, and Pinatubo in the Philippines. And so what you see here, this is what is plotted here is called the reduction in solar radiation. So that means the reduction of the amount of energy that comes into the Earth. So what is the percentage? So what you see, the dot is I think it's every month. And so what you see here is that after big eruption like El Chichon or Pinatubo, the reduction in solar radiation is about, initially it was very large, like about 4% in this case. And then, but it stays there for about a few years. Notice that, for example, here is 1983, and it doesn't return to normal until about 1986. So it stayed there for about 2-3 years, okay? So during these 2-3 years, the amount of energy coming from the sun is actually less. And as a result, the Earth cools a little bit. And same thing here with Pinatubo. It also takes 2 or 3 years before it can do that. Right? So this is the natural way of cooling the Earth. But this is also the human way of cooling the Earth. Right? So we know this urban pollution, and the pollution is very complicated. Now, of course, you cannot understand this graph, but that's okay. It just shows that it's very complicated, all the different gases and the particles that will absorb or cool the atmosphere or heat the atmosphere and so on. So it's very complicated. So there's the effect of these particles on the climate. So therefore, what you see in here is a result of both the natural and the human-induced activity, the temperature. And if you still don't believe this, then people say, okay, well, let's do some experiments. Let's compute the temperature change if there were no human activity. Okay? So this is two calculations. What's plotted here, the dashed line, is what is measured. So from 1900 to today, so the dashed line is what you measure. And then if you do a calculation, you solve a whole bunch of equations, and then you calculate the temperature, it's in the red line, if you include human influence. Now, if you only include the natural variations, then you will get the blue line. Now, you notice that if you include only the natural variations, then you could get the volcano, right? The El Chichon and the Pinatubo, you include them in there, then you get this cooling. Of course, even if you put in human influence, you still get this cooling. But you do not get this continuous rise, which is what's observed. So therefore, if you only have natural forcing, natural variations, then you will not get this one here, this rise here. And the reason why you get this rise is because of the human influence. Okay? Now, so this is why we say that you cannot just say that it is because of natural variability that causes what we observe in terms of the temperature. Okay? So, of course, you know the effects of global warming. We all lose polar bears, but people don't care. You can lose all the polar bears in the world, I don't care. But you should care, and you should care about this one here. The glaciers in many of the places have shrunk. So these are two examples of two glaciers that have shrunk. And you say, oh, I don't care because I don't live in cold countries. I don't care. What about droughts? Right? People say in Hong Kong we have the Dongjiang River, so we don't have to worry about it. But Dongjiang River will one day be dry. Right? If you have climate change. So you need to worry about this. And of course, accompanying the droughts, you will have wildfires, and you see the fires becoming more extreme in Australia and in North America. Now this one you have to worry. This is in Hong Kong. 2008, you have the flooding because of the heavy rain, the changes, the increase in the occurrence of heavy rain. So you have to worry about this. And then you also have to worry about this one here. This is sea level rise. This is a picture taken from a hut in an island in the South Pacific. When 50 years ago, when they built this hut, they were able to stay dry throughout the year. But now, every day, when the tide comes in, during high tide, your house is flooded. Every day you have this flooding, and because of sea level rise. Okay? So speaking of sea level rise, you can look at this, and it's not small. So if you look at the global sea level between 1993 and 2014 as a global mean, then you see that of course there's this oscillation every year, but what you see here is that there is a trend of about 3 millimeters per year. So in one decade you have 32 millimeters, so it's 3.2 centimeters. And so you can calculate how much it will rise by the end of this century. And so that's the global mean. This is in New York, very similar numbers. So what I show you here is the average trend is about 3.2. And in the New York area, it's about the same. It's about 2.8. And in Hong Kong, very similar. You have a rise of about 2.8 millimeters per year since 1950s. So you have this rise in the sea level. Now, one of the reasons why you have this sea level rise, one is because as the temperature increases, the water absorbs more energy, so therefore it expands, so therefore you have sea level rise. But the other important thing is that the Arctic sea ice will melt, because the temperature rise will lead to melting of the sea ice in the Arctic. So this is the Arctic summer sea ice extent. So you can see from 1900s, which is around here with about 10 million square kilometers, to today, it's only about 6 million. So there's a 40% decrease in the amount of sea ice in the Arctic. And as a result of that, you will have this, what I showed you before, the sea level rise that I just showed you earlier, and this is what I show you in the shorter period of time. All right, so the third effect of global warming is the rainfall. All right, so I told you about possibility of droughts, and this is what you see here, but possibility of also heavy rain. So in between 1901 and 2010, the blue areas indicates areas where you have an increase in the rain. So the color is called the trend. The trend is millimeter per year per decade. So how many, what is the rainfall per decade? Okay. So what you see here is that many of the areas have an increase in the rainfall. And so as an example, last year, 2014, UK was the wettest winter on record, where the southeastern part of the UK has the amount of rainfall that's more than 225% of the 1981 to 2010 average. So there's a lot of rain in the southeastern UK, which led to lots of flooding. And in Hong Kong, very similarly, you have an increase in the rainfall, although it's not very much in Hong Kong. It's 36 millimeter per decade, so it's not very much. But if you look at this heavy rain, now, so this is the hourly rainfall of 30 millimeters, and we all know in Hong Kong that if you have 30 millimeters, this is the yellow heavy storm warning. So it's, but similar data can also be found for the red storm warning and then the black storm, but the number is not very large, so therefore they decided to put this out. So this is 30 millimeters. So what you see here is there's an increase, and the number of heavy rain days has an increase of about 0.2 day per decade. So in 100 years, you will have 2 days more every 100 years. So because of that, there is something called the return periods, and what it means is that how often the type of rainfall will come back again. Okay? So what we plotted here are two. So what it means is that if the 1 hour rainfall is greater than 100 millimeters, how often can it come back? Can it occur? So if you look at this one, the blue bar means that it's in 1900. Then every 37 years, you will have one chance that the hourly rainfall is greater than 100 millimeters. But in year 2000, it decreases to about 17 years. And similarly for the 2 hour rainfall and the 3 hour rainfall, very similar results, that the return period decreases means that these heavy rain events will occur much more frequent. Okay, so now so much for what we have observed. So what we can expect in the future. Now, what we have plotted here is something very strange called the RCP. RCP actually means it's called a representative concentration pathway. Nobody understands what it is, but basically you can think about this, that the higher the number here, that means the more greenhouse gases that you put into the atmosphere. Okay? So basically, 8.5 means that if you do nothing today, you just let it go, what we call business as usual, that if you do nothing and just keep burning your fossil fuels and keep spewing out CO2 and so on, this is what you expect in terms of the temperature. All right? So this is by the end of the century here, and this is basically today. Now, what you see here is, let's look at this RCP 8.5. So the temperature rise will be up to about 4 degrees. Now this number here, 39, what it means is that this is a calculation from 39 different mathematical models, computer or weather climate prediction models. Okay, and so of course each one will give a little bit different, and so the shading here indicates the range of temperatures that you can expect. So some models, some computer models may predict to rise to as much as 5.5, and some predicted to rise about 3 degrees. So basically, what you're thinking is that if the Earth will be rising to about, on the average, about 4 degrees by the end of the century. Now, if you are really serious about global warming, and then you say, okay, well, let's do everything we can, minimize the amount of CO2 that you can put in, and then by the end of the century, you will get this blue line here, which is called RCP 2.6. And then you will get this one here. With 32 models, you will get something like this. Still, it will be warmer than today. Okay, so that's why you might have heard this 2 degrees threshold, is that if you go beyond 2 degrees, then, so that's why when people want to do is to keep this to below 2 degrees. Now, but this is the global average. If you look at different parts of the globe, you have a very different story. So on the left is RCP 2.6, and the right is RCP 8.5, which is what we're plotting here is the change in the average surface temperature between 1986 to 2005 to 2081 to 2100. So on the left-hand side, and the colors, the redder the color, the higher the temperature increase. So on the left panel here, you see that everywhere in the world, except maybe a little bit here in the North Atlantic, everywhere is warm, and in particular, it's much warmer in the Arctic and in the Antarctic. And this is especially the case if you look at RCP 8.5. It's very dark in here, and if you look at the scale at the bottom, that means in the Arctic, if you don't do anything, by the end of the century, the temperature will have risen by about 10 degrees. And of course, one of the reasons is because by that time, all the ice will have melted. So therefore, the temperature increase will be a lot more, because ice is a very good reflector of solar radiation. So if you have ice that reflects the sunlight, and it doesn't heat up the Earth or the atmosphere. But if you don't have any more ice, then you will have a lot of this heating. So that's why the northern part heats up a lot more than some of the other parts. And in our area, you will still have a warming of about 4 to 6 degrees in here. So it's very significant warming. So Hong Kong Observatory also has done a projection, and so this is the projection, and you see that the projection ranges from about, again, there's different models given different projections, so you have a range of about 1.7 to about 5 degrees by the end of the century. Okay? And they also have done this in other places. What is plotting here is called the cooling degree days. That means how many days that you need to cool your city. Okay? That means it's hotter. Then you need to cool it. Heating degree days means how many degrees above the average that you need to turn on your heater. That's called the heating degree days. So what you see here is that it doesn't matter whether it's in New York, Chicago, Dallas, or LA. If you look at this one here, the blue is the historical. So if you look at the cooling degree days, the blue is the historical, the purple is the high emissions. And so you see as you go from historical to low emission and high emission, the number of cooling degree days increases, the number of heating degree days decreases. So that means you need to turn on your air conditioning more because the cooling degree days increases. That means the atmosphere gets warmer. That's why you need to cool more often. But then also at the same time, because it's warmer, so therefore you don't need as many days to cool your home. And so the heating degree days decreases. Okay? And in terms of rainfall, you see that it's more variation in there. Some of the places so the brown means that there is a decrease in the rainfall, and the green means that you have more rainfall. So for the low emission scenario, you have some change, but not very significant. But if you have this high emission scenario, you have lots of rainfall in the Arctic, but there are also many areas where there will be a lot drier, so there will be more droughts as well. Now for Hong Kong, the projection is something like this, and you see that this variation is a lot more than temperature because rainfall is a lot more difficult to project. And so sometimes you could have very low rainfall like this, and this will be a drought. And you think about this, that if there's a drought in Hong Kong, that means there's a drought in Guangdong, and the Dongjiang River will not be able to give you the water. So you need to think about what to do. Lastly, about the sea ice, if you use the worst scenario, then the amount of sea ice will be completely gone by the later part of this century. And so if you have you can control the emission, then you can still maintain some of the sea ice in the Arctic. And because of the warming, you will have the sea level rise. Again, this is different projections. And so the worst scenario is actually 1 meter above what's today. Okay? So 1 meter, you imagine that 1 meter in Hong Kong by the end of the century. And so all the subways, we have to think about all our MTR subways, all our car parks, all our underground shopping malls and whatever. You need to think about what to do with that. And so for this, something called the extreme sea level, that means suppose you have a typhoon coming, they give you an extreme sea level rise. And so we are plotting again what we call the return period, again how often it will happen. So for the current it's in the blue, and if the rise of sea level is about 0.18, it's in the red, and the green is half a meter. So today, for example, if you have how often do you get a 3.5 meter rise? It's about 35 years, okay? But if you have a rise of 0.18 meters, it will happen every 15 years, and if it's a rise of about 0.6 of a meter, it will happen every 2 years. So every 2 years you will have a extreme sea level above chart datum. Right, so the last thing I want to show you is this very interesting thing from National Geographic. So they did a calculation and say, let's say if all the ice on overland has been melted, whatever the reason is, okay, global warming or whatever. So you have all the ice being melted. So what happened to the Earth? So the blue means that it's water. So the green will still be, or brown will still be land. So what do you see in here is that the large part of China is gone. Much of that Vietnam is gone. And if you blow this up for Hong Kong, it's no longer there. And many of these places will not be there anymore. But of course, this will not happen for another 3,000 years, so you don't have to worry too much about that. Okay, but the message here is that if you have sea level rise, some of these places will be flooded, will be submerged. It will no longer be there, and so you need to be prepared for this. All right, so to summarize, then this is what the kid wanted to ask the professor, and then the professor's answer I want to tell you is that it's enhanced by human activities, and we must do everything we can to slow down such warming. And that's why we form our School of Energy and Environment. So thank you very much.
So we can start our Q&A session. Do any one of you have any questions would like to ask Professor Chen?
May I use Chinese?
Yeah.
Thank you。我想问一个就是比较技术上的问题，就是前些年也有一些专家提过，就是可以在地球上的某些地方装上，比如说很大的镜子，通过提升它的反射，然后减少它对外界能量的吸收，来降低这种升温的可能性。然后不知道您是怎么看
Okay.
Thank you.
Good point. So the question is, if you can you do so? Let me answer in more general terms. Okay. So the question is, can we do something about this global warming? So the question is, if you put a lot of mirrors above the Earth, can you reflect the solar radiation? So this is a topic called geoengineering. So a lot of people are thinking about this, what to do, and so one possibility is to put these mirrors, right? And of course, other people would say that, okay, well, because some of the aerosols, I show you that some of the particles will absorb solar radiation. And one of them is called sulfur dioxide, right, or sulfates. So in fact, for the two volcanoes that you saw with the cooling, most of the cooling is due to the particles as well as sulfates that are shot up into the very high up into the atmosphere. So in fact, one of the Nobel Prize winners actually suggested, let's shoot up a lot of sulfates into the atmosphere and then cool the Earth. So that's another geoengineering possibility. So yes, it is possible, but two things that you need to think about. One is, how much does it cost to have an effect, right? So you need to do a calculation and say, how much does it cost to do all that? Whether it is putting sulfates into the atmosphere, or putting mirrors, or doing other things. The second question that you have to ask is, will there be unintended consequences? Okay, you don't know what will happen. So because the Earth is a system, right? And we all know, I mean, you know that a system has many, many components. And these components are not what we call linear. So it's not just that you go 1, 3, 3, 4 like that. There's this feedback. And so if you change one component here, then yes, it might cool the Earth, but there might be a feedback to the previous part. And how it fits back, it's very complicated. And so yes, people have done this, and in fact they have done calculations and say whether it's possible. And it is possible that some people are talking about this, but if you want to do it on a large scale, on a global basis, the cost, I think it's prohibitive.
Isn't it easier to convert back CO2 back to the basic, reduce the CO2 level, like with different factories like nuclear induced factories to reduce the level of CO2?
Yes, it will be cheaper. It will be cheaper than geoengineering. That's true. So people are talking about, well, how do we reduce CO2, right? So one is you use nuclear. And that has been talked about until Fukushima. So after Fukushima, everybody was nervous. And so whether you would have a renewed interest in terms of nuclear. But of course, China doesn't care. China is still building lots of nuclear power plants. And in fact, if you talk to our president, of course, then he would say that it's all human errors. All the previous 3 big nuclear accidents are all human errors, right? 3 Mile Island, Chernobyl, Fukushima. They are not because of the design of the nuclear power plant. It's all because of human error. So if you design a system such that you can prevent the human error, then nuclear accidents could be prevented. But of course, you also need to think about the nuclear waste. What you do with the nuclear waste? So that's another issue. So yes, you can reduce CO2 emission by using nuclear, but that's only for electricity. You still need to think about transportation. Transportation contributes quite a bit to the global warming. Everybody drives big cars, the trucks, and so on. And also, in driving that, not only you get the oil from the ground, and when you get the oil from the ground, you also emit methane. So unless you have all cars to be electric, and all the electricity being generated from nuclear or renewable, then you will still have this. But the other thing that you can reduce CO2 is something that people have been talking about. It's called CO2 capture. So what you do is all the CO2 that's coming out from power plants, you can capture that, and then you can reuse the CO2. Some people say you can capture it, make it into liquid, and then transport it somewhere else, put it in a cave for the next 100,000 years, and you can forget about this. Right? So that's one way. So it's in fact, China is thinking about having a pilot plant like this in Guangdong, actually, to capture the CO2, make it into a liquid, transport it, and put it in a cave. So this is one way. Some other people are thinking that you capture the CO2 and then convert it back into something useful. So there has been some efforts in that area, but CO2, the reason why CO2 is such a big problem is because CO2 stays in the atmosphere for 100 years. If you generate one molecule of CO2, it sits in the atmosphere for 100 years. Because the bonding between the two oxygen molecules and the two oxygen atoms and the carbon atom is very strong. If you want to break that bond, you need to put a lot of energy. And so that's why it's very stable. And so, but people are already thinking about ways to do this. I mean, the plants have done this. All the plants break down the CO2 to make plant food, right, through photosynthesis. So that's what plants do all the time. So if you can mimic what the plants are doing in breaking down the CO2, then you would do the same thing. So there's something, actually a study, very many people are doing what they call artificial photosynthesis now. So it will be another way to do it.
What about human population? People like to use, because the human is one of the factors that affecting the climate change.
True. So if you kill a lot of people, then you will have you will not have. Actually, I was just half joking, because every time that's actually one reason sometimes that you see this decrease in the CO2 is because like if huge famines, for example, that kill lots of people, then actually the CO2 will go down, and so you need to control the population. That's for sure, because the population is not only generate more CO2 because more people need more food, so you need to grow more food. But when you grow food, and then one of the sources of methane is actually when you grow rice, you actually emit methane, or if you eat beef, right? So if you the amount of methane that's produced from raising cows is tremendous. So the type of food that you eat will also affect the amount of CO2 that you have. So yeah, you can control the population, but I don't think there's an optimal population that you. I mean, even if there's one, that you can say, okay, well, this is optimal, so you cannot have any more children.
Dr. Chen, how confident we should believe those data?
Which data?
Well, you talk about the CO2 level, you talk about the temperatures, and those...
In the past, you mean?
Yes. Of course, you mentioned about the way to getting those numbers through the iceberg, through the soil, through the, but it seems not really convincing to come up with a very accurate numbers. But in fact, when we see the trend, it seems they are quite aligned. It looks like a manipulated data, so that those two lines looks like the same, and make people believe that this is a real threat on the human Earth of this century. But when you talk about the 40,000 cycle, it seems it's nothing. So, is it a joke or what?
It's good.
Thanks.
It's a good point. I plot this to show you. In fact, the CO2 alignment with the temperature, there is a very large uncertainty. In fact, some people have said that, or another theory is actually that the temperature rose first, and then you have the CO2 increase. Okay. Now, so there are many theories of that. So, for example, one theory is that when you have a temperature rise, then you have more animals. There were no humans at the time, so the animals therefore emit more CO2, and then when you have temperature rise, then you have the water evaporating, so therefore you have more rain, and so therefore you will have more plants, and then so there's lots of theories. In fact, contrasting theories. But if you look at, even if you say, okay, whether it's because which one comes first, I think that's not the main point. The main point is you think about this. The message what I want to show you in that one is that in the last 400,000 years, the temperatures did go through cycles, and that is whatever data you look at, you will see this cycle. Okay. Now, the point I wanted to make is, yes, you have seen these cycles before, but today, with that much CO2, why are you not seeing a much higher increase in the temperature, right? And the reason why you don't have such a simultaneous increase in the temperature is because you have this counter effect of pollution. So if you don't have pollution, the amount of temperature increase will be a lot higher. So that's my point, is that when people argue that this is all natural, they have missed the point that it is not natural, because if you only look at natural forcing, you cannot produce this temperature trace that we have observed. So, yes, there's a very large uncertainty in the paleoclimatological records. True. But that's not the point of my showing the graph. It's just to tell you that there is this oscillation. And this oscillation is there. Whatever data you look, wherever in the world that you go to, you see very similar things. I mean, there will be uncertainties, but by and large, they will be the same.
So a follow-up question.
Yeah.
Right now we are in a stage like in those years we talk about global warming.
Right.
If this is a cycle that maybe 100 years after there will be a global freezing.
Yeah, that's true. Now.
So that's the points come up with some people say why people stress on global warming, because there's a lot of business going on behind it.
Right.
The carbon
Right.
trading, energy efficiency projects, all these things goes on, and people want to do more business. That's why they try to threat the people, let people do something because of this global warming.
True. It is. There has been. Your point is correct that if you don't do anything, it will eventually come back down. That's what. If it's a natural cycle, okay. So this is a natural cycle like this, right? But the problem is the warming by humans, it's going faster. See, right now we're actually on the rising trend. Even in the natural cycle, we're in the rising trend. But it's rising much more rapidly because of the human activities. So the point is, if it continues to rise, there might not be a mechanism for it to come back down. See, the mechanism for it to come back down is that one argument is that if it's very warm, okay? If it's very warm, lots of water vapor gets into the atmosphere, lots of clouds form, okay? So much so that it will block the sunlight, and then the Earth will eventually cool. So that's one argument of that it will not warm forever. So the argument is how if you continue to have this rise much faster than what you have expected in the natural cycle, then the Earth system may not have enough time to adjust to this warming. So if there were no human influence, it will come back for sure. But if you have a lot more warming, then it may go to a point where the Earth cannot have enough time to adjust to come back down, so it will continue to go up. It's like in a stable versus an unstable system, right? So if you pull a string, pull a spring, if you pull it not very strong, then you release it, it will come back up. So you have this simple harmonic oscillation, right? You're an engineer, you know this. So, but if it's an unstable system, you pull it so much, the spring will break. So it will not come back up. That's what people are arguing. And when you say, are there business, it says because of the business driving it? I don't think so, because the biggest business lobby today is actually from the oil companies. That in the U.S., the U.S. is the biggest, the largest country that is not supporting any work on climate change, because there are many oil companies and coal companies that are lobbying the government not to do anything so that they can continue to sell their oil, they can continue to sell their coal. In fact, with the exploration of the shale gas now, there will be even more stronger pressure and say you don't need to worry about worry about global warming because it's not real. And the reason is because they want to sell more of their shale gas and sell more of their oil. So if you talk about lobby, it's the lobby from these companies rather than from those who are selling energy efficiency equipment. They are peanuts compared with the oil companies.
Yeah, I'm just curious that when we predict the future scenario using the model, right, based on your major data, you do the calibrations. In the same manner, can we also do those past data 10,000 years ago, right? Can
yes.
we also, based on the estimated data, can we also do some verification?
Yes, people have done calculations back in the last 10,000 years. And of course, when you do past 10,000 years, it will not be as accurate as what you have because you don't have that much data.
Right.
But they have done this, and the temperature trace is very similar to, it's not exactly the same. There will be differences, but by and large, you will see this.
Yeah. So my second question is, recently I read an article from the South China Morning Post that in Hong Kong, urban heat island effect also caused the global warming very significantly. So the one question, like when we have some the material to reflect the light, and then so my idea comes out that when we implement rooftop garden, also when we look at the albedo coefficient, the water can be as high as up to 1. So do you think if in Hong Kong, if we have a rain garden, do you think it can be also a significant kind of measure to eliminate the UHI and also the global warming?
Yeah. This will be measures that you can do. Certainly.
Professor Chen, personally, I would like to know your personal comment on what is the best method to reduce the level of carbon dioxide. For example, by government policy to regulate the production of cow, because the waste of cow, I think, emits the most of CO2 to the atmosphere. And the second is emission trading. Is good for use because it can control the production of between the nations. And the third one is how about controlling the carbon footprints of all the citizens? Yeah, or any other comments that you prefer the best?
Yeah, very good question. Yes. Anything that you can do to reduce carbon will be good, and so yes, you should eat less beef because it's not very healthy for you anyway. So that will reduce the amount of methane that's come out. Whether it should be government regulation, government should do more in terms of regulation. That's true. So, for example, Hong Kong has had this mandatory energy efficiency ordinance that requires new buildings to meet certain standards, but it could be much more. They should provide more incentive for people to reduce energy consumption through energy efficiency measures. And so you can have incentives and you can have regulations. So both of them should be done more. So anything that you do that can reduce emission, for personally, there are lots of things that you can do, of course, right? So you reduce electricity consumption very easily by turning off your lights and making it your room less cool, and if you are in a mall, just complain that it's too cold, and in restaurants and so on. So everything that you can do. Emission trading is something that's very debatable, because emission trading means that you can continue to emit a lot of CO2 if you have money. So it's a bit controversial as to whether, I mean, in the long run it's not going to work, but as a short-term measure, then you could do something like this, but eventually you should just reduce overall. So I don't think it will be a good way to reduce the total amount of CO2. It's not as efficient as having a reduction of the consumption of energy. So,
any more questions? Okay, no. Thank you, Professor Chan, for today's fruitful sharing. So this will be the end of our today's session, and our next session, our next lecture will be in April about movies. So I hope we can see you once again. Thank you for coming. Have an enjoyable evening.